In the context of multi-criteria evaluation or multi-criterion decision analysis or multi-criterion decision making, our objective is a single objective. We are concerned with where are the areas that are suitable for Kudzu, right here. So that's our overall objective. And we'll look at 3 models to satisfy that objective and to create a decision set from each of those. One is a relational conditional model, the other is a weighted linear combination, and the last one is a fuzzy logic based model. And these are reproduced from this paper, from a 2014 paper by Qi et al. That looked to determine suitability for Kudzu in the United States. And you'll find this reading, and it's a good idea to read it over quickly or peruse it, in the Module 5 section for the modeling. Kudzu suitability is our objective. For our decision frame, we have to find the habitat suitability for Kudzu in the continental United States, excluding Alaska, and any of the islands, maybe some of the islands are in there, I can't remember. So that's our region, our decision frame. We'll have factors that go into that, factors that are known to be affecting the ability of Kudzu to establish and reproduce. It mostly reproduces vegetatively through its rhizomes. So that means one plant can be basically kind of a large region that's just a single plant, a clone, for example. So we'll look at precipitation and growing degree days, as well as the presence of Kudzu, because Kudzu nearby affects the probability of Kudzu establishment nearby. Constraints I have here is none, but really in the Boolean case, constraints and factors are the same thing. So that has to do with standardization. So each of the factors has to be standardized so that the meaning of 0 and 1 is the same across all of the factors. So precipitation, a value of 1, let's say, is the same as a value of 1 for growing degree days, the same as a value of 1 for presence of Kudzu, for Boolean. For rescaling, same thing. In this case, we don't have just 1s and 0s, but we have 1, 2, 3, 4, 5, or 1 to 10, or 1 to 100, or 1 to 200, whatever type of relative scale we want, as long as the values, let's say, of 2 are the same across the factors in sense of their meaning. Fuzzy, on the other hand, we use functions called fuzzy functions or membership functions to fuzzify each of the factors into a likelihood, or likelihood at the end, but each of the factors into membership in the idea of suitability for Kudzu establishment and propagation. We also have to consider weighting. We'll look at equal weighting cases, but we might try changing the weights as well to see what would happen to the output. Now, once we've done the standardization of the factors, we have the factors, we standardize them, then we decide what decision rules to do. We'll have 3 decision rules. One will be Boolean and, so that's for the Boolean case, a weighted overlay for the rescaling case, and a fuzzy overlay for the fuzzy fuzzification or fuzzy variables to create an overall likelihood. Likelihood for Kudzu. That's what comes from fuzzy. At the end is a likelihood, a value that ranges between 0 and 1 for every single decision set cell. The closer it is to 1, the more likely it is that Kudzu will establish or can establish or is established there. The closer to 0, the least likely it is that Kudzu will establish in that location. And then finally, we have to consider sensitivity analysis. So sensitivity analysis means that each of the decisions that went into these two parts of multi-criterion evaluation, the factors and their standardizations, or the decision rules we use to put them together, any change there can change the output decision set. So that means the map of Kudzu establishment is a function of the decisions we make up top. And if we change a decision, the output may change. And we have to be aware of that. And often we test different scenarios of changing certain things within, let's say, the standardization, or within the decision rules that combine the factors together to create the decision set. And then we see what that might look like in other scenarios. Because remember, we're creating models, and the models we're creating are just approximations of reality, and they're dependent on the decisions that go into the modeling. And what factors are the outputs most sensitive to? And that's a very important question. So if you recall the model building process, so this is this here is the formalization of what happens within the factors and the standardization of the factors and the decision rules. So first we set our environments, and we have a large data step here to do to create the data necessary, the raster data necessary to do the modeling. And we'll have to set environments twice. Once first to control part of the data step, and once we have a raster layer, we go back and reset environments, and then go down to conceptualizing our process, which is conceptualized for us because we're repeating analysis that's been done previously. And we'll do both models in Model Builder and Python statements to create Python programs or scripts to do the all of the data manipulation, as well as the decision rules and standardization of the factors and constraints. So the first thing we have to be thinking of here is that based on previous studies on Kudzu, its distribution, it was determined in 1970 that the minimum annual precipitation needed for Kudzu to reproduce, establish, and propagate was 1,500 millimeters per year, so 1.5 meters of precipitation per year. And the minimum number of frost-free days was 146. So you had to have 146 days without frost and quite a bit of precipitation. And so the first models were based on this, which means that we need a layer to show precipitation here, and we need a layer of frost-free days. And with that, we could put this particular set, or these particular thresholds that are determining the standardization of the variables, precipitation and frost-free days, together in a Boolean operation, so a decision rule, which is Boolean, to create a modeled output of where Kudzu should be, or is, or will be. So data requirements for all of our analysis then are going to need precipitation and climate data on frost-free days. And we're going to use 1981 to 2010 US climate normals. A climate normal, is just a long-term average of monthly, daily, etc. temperatures or precipitation. So you can have you can have normals which are based on months, you can have them based on days, based on hours, whatever. As long as it's over a long period, so a 30-year average is the kind of standard, or approximate 30-year average in any case. And the data I got from here. Now our data is all as points, because these type of data are measured at climate stations. So this is what the climate data looks like. It's a bunch of points, which we can't do much analysis with by itself. The climate data, so we make our little table. We have a layer for climate. We also have a boundary, which is the boundary of the southern, or the continental U.S. Without Alaska. And we also have the locations of observed Puerria montana or Kudzu colonies in the United States. So in the west and mostly in the southeast United States and eastern seaboard up to New York and even Pennsylvania. They're all in the same spatial reference. They all have a vector format, so none of them have a resolution per se. So we're going to have to convert everything to raster before we can do analysis. So there's going to be a conversion step that's required. Except for climate, we won't be just doing encoding. Climate will not be encoded. We'll see that we're going to interpolate climate to create a continuous surface of growing degree days and mean annual precipitation. So climate, because it's a continuous variable, we can, and it's measured at discrete locations in space, we can interpolate that. So it becomes, these points of climate become what's called a support or spatial support for a continuous field to be estimated from those climate points because they are frequent and dense. And we'll choose the resolution that we want based on that climate data. So what resolution do we want to do, or do we want to use to analyze the entire United States? And that's an important question here, because too large of a resolution will just dilute any of the variation in climate that might be important to Kudzu establishment, and too small of a resolution means it'll be computationally intractable. Our computers won't be able to do the analysis or do the interpolation of the climate data because it's on such a small cell size. That means there's so many of them that it just takes so long it's not worth doing. So we're going to use a 1 kilometer size, and that makes sense for to look at variations in precipitation, because as you know, within a kilometer, when it is raining, depending on the type of system that's overhead, you can have rain a kilometer away from campus and never see a drop on campus, for example. Precipitation is very localized often in its effects, depending on, again, on the type of weather system. Some weather systems are very large, and so it'll rain just everywhere. And some of them are much smaller, so you get very localized pockets of precipitation. And so we'll use a 1 kilometer grid level size or cell size in order to better represent the variation in both precipitation and number of growing degree days. And we can do that because we have such a dense network of climate stations in the United States. So before undertaking any analyses, we have to decide, okay, well, what is the cell size? And we said it's a kilometer we're going to use. And also, what will be the region of analysis? And we know that's the southern continental United States. So the excluding Alaska, I'm just going to say the U.S. from now on. So we have a boundary for the U.S., and the boundary is vector, and we're going to set our environments to match that boundary initially. So we'll set the output coordinate system, the processing extent, and analysis mask to match that boundary. That way, any rasters that are produced will just be produced with values that are non-NA inside the boundary of the US. Everything outside of it will be NA values, so we won't see them. We'll see the shape of the US country. So we set those first. Then we interpolate our climate values like precipitation. So within the climate data, there's a column called precipitation and something. I can't remember exactly what we called it, but we'll see it when we do the example. So there's a precipitation column and a temperature column. And we're going to use what's called the Topwater Raster tool. And that's because we have a very dense network, and we can treat this dense network as if these climates values were elevations, spot height elevations. Because we can have a lot of local variability, in these climate stations, we want to be able to model that variability at a very fine scale, but also over the entire United States. And there's a few techniques that can do this effectively. Topwater Raster is a particular type of tool based on ANUDEM by Michael Hutchins in Australia, which is the state-of-the-art algorithm used to create topographic maps from elevation data, contours, or spot heights. And we can say that our climate surfaces are just like elevation surfaces. Although it's not elevation, it's going to be temperature or precipitation. It doesn't mean anything to Topwater Raster, right? It's our conception of things that matter here and the tools we use. Other types of tools would overly smooth the climate fields because of, and we don't want to overly smooth things because we'll lose that fine scale variability that can be very important in understanding where Kudzu can establish and propagate. So in the geoprocessing tool, we'll go through that when we do it. We'll do a Topwater Raster. We specify a couple key things in this tool. One is the field that has the numbers that we want to interpolate into a continuous representation of the values. So we go from points to this down here, from a discrete to a continuous field. We specify our output cell size. And we also specify the type of data that's going in here. So we just say the type is point elevation and the primary input data is spot heights. And that's pretty good for what we need to do. So we can actually see here when we do produce that, the Topwater Raster output is the bottom one right here. And you can see fine scale variability in precipitation being represented here, where you have dry areas, and then in the Laurentians and stuff, and the Appalachia, you have some really wet areas where you get precipitation or graphic effects of precipitation. Of course, in Florida, the Southeast, and these states here, you get a lot of the Gulf air masses. This is what's causing the precipitation mostly there, and that even goes up into into Canada most of the time. So we get that type of precipitation. It's all coming from that type of weather fronts. And so we have that wet east because of that, much wet east. And then, of course, you get into areas into the plains regions where you have semi-desert conditions and even real desert conditions in Texas and Arizona and stuff like that, and California, where there's hardly any precipitation. And then you get to, of course, the coast, where we have coastal rainforest conditions. And the zones here, so the type of growing zones here, like in 9A, are the same ones you find in Florida. And this is why you'll find palm trees and stuff in Vancouver and Victoria growing just fine, lemons, some oranges types and stuff like that. And you only find those here in this region, because you have the same type of, although you don't get very high temperatures in the West usually, except in the past couple of years, but the winters are very mild. So mild enough that you can, your average daily high can sometimes be around 7 degrees, 6-7 degrees in January. So very good climate for growing things, and obviously Kudzu would love it there. Once we create that particular raster layer, then we reset all of our environments to match that raster layer. So all of the key environment settings now we reset to match the precipitation which is the output of the interpolation by Topwater Raster. And that's so when we do our next Topwater Raster, and we can also do that in Python, as you know, mentioned many times. But then when we do the next Topwater Raster, which is for the growing degree days, we'll be ensuring that that raster will exactly match the precipitation. The cells will all align, etc. So we set everything. Once we set out all those environments, then we do a Topwater Raster again for the growing degree days. So these are days less than 0 degrees Celsius. We do the same settings as previously. And we click OK, and we get a value, a layer that looks like that at the bottom there. Where you can see again, green here just means very few days less than 0 degrees Celsius. And you can see there's spots of no days less than 0 in these regions up here. You know, near where southern Vancouver Island is, and then you have Washington, and in there Seattle and stuff like that, just like Vancouver. Then with that layer, because it is the days less than 0 degrees Celsius, and we want to know days more than 0 degrees Celsius, that's what the growing degree days are, we take 365 days minus the previous raster, and that gives us days greater than 0 degrees Celsius. So 365 days, that's the number of days in a year, the average year. Or I think all of them, I think except leap years maybe, but 365 minus the days that are less than 0 degrees, because that's the data we have. That creates our days above 0, our growing days, frost-free days, I should say. Then we have Prairie, Montana. These are the locations of current Kudzu observations in the United States, and you can see there's a few up there in the west, still under control. And we have to convert this to a raster layer so that we have cells representing the presence or absence of a Kudzu observation. And all we care about here is not how many Kudzu observations there are within a 1 kilometer cell, but whether there are or are not. So when we use 1 kilometer cells to count the number of points, or to count the presence or absence of a Kudzu observation, we will have less cells coming out this end with positive Kudzu observations than there are actual Kudzu observations. So let's say there was 100 Kudzu observations right here, 100 obs. When we do that in a 1 by 1 kilometer cell, let's just say that's a 1 by 1 kilometer cell, you can see maybe there's 100 Kudzu observations in there, but over here that cell will just register as a 1. Presence of Kudzu, not how many Kudzu, but just presence of Kudzu. So our count goes from 100 to 1 over here. And in this case, that's fine, because the way we care about Kudzu in replicating the paper's results is not the intensity of Kudzu. The intensity is the number of points per unit area. But what we care about is whether or not Kudzu is present, because if it's present, then there's a higher probability that a cell nearby will have Kudzu present. Once we do that, we revisit all the layers, and we finish our table, and all we're filling in now is a resolution here that we have 1,000 meter cell size, or 1 kilometer cell size.